Hi and welcome to Fibre Optics. So I'm going to have a little look at how light passes through an optical fibre and make sure we can draw the diagrams before we do any maths. Now, you're probably thinking, it's okay John, I did this at GCSE. You just need a rectangle to be your fibre optic, and then the light just goes somehow as some kind of zigzaggy line down the fibre. Job done, 3 marks. See you later, I'm off for a hot drink. Now, we're going to make sure you can draw this properly. And that means finding yourself a straight edge. A ruler would be the obvious candidate. An ID card would be better than nothing. The edge of a book. Something like that. Every time the light meets an edge, I would construct a normal. So our light comes along. As it enters the fibre, mine failed here, didn't it? It didn't bend towards the normal. When it reaches the edge of the fibre, we've got to make a decision. In this case, it's just a bit of guesswork, but we're going to say that's a large angle, so that's greater than the critical angle. If it's greater than the critical angle, we're going to get a reflection. And it must look at least visually as if the angle of incident is equal to the angle of reflection. Okay, now we need to draw another normal. Okay. And then we get to the edge of the fibre. Final normal drawn. And then we've got to bend away from the normal. So what you need to do now is to pause the video, get yourself a pen, a piece of paper, and get a really good diagram drawn like that to make sure that you can do that. So if it crops up, you're going to get full marks for that. We can remind ourselves of some of the maths that we did last time. This obviously is about it's all about finding the critical angle. So if we go back to the data sheet, we should be able to see the sine of the critical angle. Let's find waves. Is N2 over N1. Just a few reminders. We're following this line here, we're going from region 1 to region 2. So in this case, N1 is equal to the refractive index of the fibre. Let's call that 1.67, just to make sure I don't use a number that I've used later in the questions. And N2 in this case is air, so it's N2 is 1. So let's go about finding the critical angle. So pause the video, everyone calculate the critical angle for this fibre, and then we'll move on. So assuming you've done that, we've got sine theta c equals 1 over 1.67. So theta c equals sine to the minus 1 over 1.67. Let's do that on the old calculator. So it's shift, sine, open bracket, best to use the fraction key, 1 on the top, 1.67 on the bottom, move it along, close the bracket, equals 36.78 degrees. Let's round that to 37 degrees. No, let's round that to 36.8 degrees because the information supplied was to 2 significant figures. Right, we're now going to have a look and think about what happens if the fibre has a cladding. It's not really going to be completely obvious why a fibre has a cladding until we've done the next video and we actually start looking at some of the complications around dispersion. But we can certainly see how this will affect our diagram. So let's keep this as n equals 1.67. Now the cladding, we only get total internal reflection if you go from going from this material with one wave speed into a wave speed which is faster. For the wave speed to be faster, then we're going to need a lower refractive index than that. So I'm going to make this a refractive index of 1.25. So let's see what that effect that has on the critical angle. So sine theta c equals. Let's just pause there. I'm sure you can find the equation now. You can do the maths. You work out the critical angle, and then when you're done, you can unpause the video. So in this case, N2 is 1.25 because we're going from 1 to 2. This is 1.67, so I need to get the old calculator going again. It's shift sine open bracket. The top's got to be 1.25. 1.67. I've got managed to get myself 2 brackets. So let's get that in. Okay, so the critical angle has now increased to 48.8 degrees. I've just lost it. So I don't know if it's 48.8 or 48.9. I missed the number. Now that seemed like a strange thing, because that actually means that it's actually going to be harder to get total internal reflection with the cladding, and we'll come to that next time. Certainly when we're drawing our rays for the fibre, a ray travelling at the critical angle will now have to be more straight down the fibre. I've rather exaggerated that now, haven't I? But I'm making a point. And that means that it's a bit bigger. The largest possible angle of incidence has decreased as well. It's possible for a fibre, if it's bent too much, I'll draw a diagram now of a fibre with no cladding. It's possible that if we have a ray of light going into our fibre like that, again, let's quickly draw a normal. It bends a bit towards the normal. Okay, that's looking pretty good there. Still got a very large angle of incidence. Got a bit of a worry on now that this diagram's not going to do what I want, but you can't cheat sometimes. So, when it comes across to here, it's now got a much larger, much smaller critical angle, and there's a risk that some or all of the light will be refracted out of the fibre. And you'll see next time that there are situations where it's preferable that the light was refracted out of the fibre. That's a better outcome than the light carrying on down the fibre by too many different routes. Got some follow-up questions for this. I could just have one go at doing something with the laser, which I can't now find. Here's the laser. Okay, I haven't got much to go on here. There's the laser. Okay, no risk of blinding you, fortunately, because you can't do that in a video. But you can see I'm shining the laser into the end of my ruler, and the ruler is acting as a fibre optic. The light's travelling down the fibre by total internal reflection. There you see the light's coming out the end of the fibre. Okay, all the best. Bye.